So in this next section now, I'm going to get into what Bayesian statistics is, so provide some introduction to Bayesian statistics. So Bayesian statistics is really, at its heart, knowledge synthesis, meaning it formalizes the process of learning from data to update our belief about a particular hypothesis. An example that I like to present at this point is, what do you think is the chance of USA beating Brazil in soccer tomorrow? So if you were a traditional statistician and you did not believe in Bayesian statistics, what you would do is you would go to the FIFA archives since 1940 and you would look at all the times that USA and Brazil met on the soccer field. And then you find out how many times out of all of that USA actually beat Brazil. And you might estimate 1%. So that is the data-driven, without any belief estimate. And that's the traditional statistical estimate. But if you were a Bayesian statistician, you might say that all that is true and it provides us some information. But really, if you consider the last, 15 years or so, there has been a lot of improvement in the U.S. in terms of soccer. We have, kids' soccer leagues and, adult soccer leagues. We are importing players from other countries. And so there is a lot more belief that USA has a greater chance of beating Brazil. And so maybe the probability is close to 15%. And so that is a Bayesian approach to not only use the available data, but also use other information. So we are essentially combining two streams of information here. We have all used Bayesian algorithms whenever we use Adobe Photoshop. So in this example, we have a blurred image that represents the data, and we are using Bayesian algorithms to say that we believe that that is a guy looking through a camera, and that belief is updated with the actual image to provide this sharper posterior probability distribution. So this is commonly used. Okay, let me now get into the actual nitty-gritty of the Bayes' theorem. Bayes' theorem updates the probability of a belief. So in this equation on the right-hand side, we have P of H0. That is the probability that a given hypothesis H0 is true, and it is referred to as the prior probability that H0 is true. And prior meaning prior to observing any relevant evidence. And the next term, P of E conditional on H0, means what is the probability of seeing the evidence given that the hypothesis is true. And this is referred to as the likelihood. So the first term, PH0, is the prior, and you have seen that before in the decision charts. And then what is the probability of seeing evidence? That is P of E slash H0. So that's the likelihood of having seen the evidence if the hypothesis is true. In the denominator, we have P's of E, which is the probability of observing the evidence, if the hypothesis is true or if the hypothesis is not true. So we would just see something. And on the left-hand side of the equation, we have the probability of H0 given E, meaning the probability that the hypothesis is true given the evidence. And this is referred to as the posterior probability distribution. So let's do a very simple example. It doesn't actually show you any of the power of Bayesian statistics, but it's good to just run through a calculation. And so, whenever you open a book on traditional statistics, they always start off with a coin toss example. If you use a Bayesian textbook, they always start with this cookie example. So there are two bowls of cookies. Bowl number 1 has 10 chocolate chip and 30 plain cookies. And bowl number 2 has 20 chocolate chip and 20 plain cookies. And so our friend Fred picks a bowl at random and then picks a cookie at random. And the cookie turns out to be a plain one. So how probable is it that Fred picked it out of bowl number 1. Now, before we jump into the Bayesian calculations, we can sort of just use our common sense and figure out that bowl number 1 has more plain cookies than chocolate chip cookies. Bowl number 2 has the same number of each. And so it's more likely that Fred picked it out of bowl number 1. So just we don't have to do any statistics or any probability calculations to figure this out. So intuitively, it seems clear that the answer should be bowl number 1. But let's chug through our Bayesian calculations. So let H1 correspond to the hypothesis that Fred picked the cookie from bowl number 1, and H2, the hypothesis that he picked it from bowl number 2. So from Fred's point of view, at least in the beginning, the bowls are identical. And so the probability that he picked it from bowl number 1 or 2, so PH1 and PH2, they are the same. So we can say that they are both 0.5 and they both add up to 1. And then Fred observes some evidence. The data D is the observation of a plain cookie. And so from the content of the bowls, we know that the probability of observing the data of one plain cookie, if hypothesis 1 were true, is 30 out of 40 or 0.75. So that is the probability that Fred would have picked a plain cookie if he had picked it from bowl number 1. The probability of observing the data if hypothesis 2 were true is 20 out of 40 or 0.5. And so we can say, okay, we can calculate the posterior probability distribution of hypothesis 1 being true given the evidence of one plain cookie. And so in the numerator on the right-hand side, we have the probability of H1, so that's 0.5, that's the prior. The likelihood is probability of observing the data given H1 is true, at 0.75. And in the denominator, we have the probability of having observed the evidence if hypothesis 1 were true and if hypothesis 2 were true. So the first term is probability of H1, 0.5. Probability of the data given H1 is 0.75. Probability of H2 is 0.5. And probability of D given H2 is 0.5. And so the posterior probability of H1 given the data is 0.6. So there is a greater than even chance that Fred picked that cookie from bowl number 1. And conveniently, this reflects our intuition that the cookie is more likely from bowl number 1, since this has a higher ratio of plain to chocolate cookies than bowl number 2. Let's go through one more example. And there's somewhat of an unrealistic example where we are using Bayesian statistics to decide the guilt of a defendant. As far as I know, Bayesian statistics are not used in courtrooms, at least not in the US. So here we are looking at the event G, that the defendant is guilty. And E is the event that the defendant's DNA matches the DNA found at the crime scene. And so what is the probability of observing this evidence if the defendant is guilty? So that's the likelihood. So P of E, given the hypothesis is true that the defendant is guilty, so it's the probability of seeing event E, assuming that the defendant is guilty. And usually this is, in the case of DNA evidence, taken to be unity or 100%. So if the defendant is guilty, you're more likely to see the DNA match. But now, what is the probability of guilt given that there is a DNA match? So this is the posterior probability that we are interested in. And then the last bullet is, what is the probability of guilt? So this is the initial or prior probability. That's the juror's personal estimate of the probability that the defendant is guilty based on other kinds of evidence than the DNA match. So this could be based on the defendant's response under questioning or previously presented evidence, or just the juror's personal biases. Suppose the juror decides that there is a 30% chance that the defendant is guilty. So this is what would be called the prior probability assigned by the juror. And now let's suppose that the probability that a person chosen at random would have a DNA that matched that at the crime scene is 1 in a million, so or 10 to the power minus 6. So the event E, the DNA match, can occur in two ways. Either the defendant is guilty, the prior probability of 0.3, and therefore his DNA is present with probability 1, or he's innocent with a prior probability of 0.7, and he just happens to be unlucky enough to be the 1 in a million matching people. And so the juror could now use the Bayes formula to revise his opinion to take into account the DNA evidence. So the posterior probability, the probability of guilt of the defendant given the evidence of DNA match, is in the numerator we have the prior probability 0.3 and the likelihood, which is 1, the likelihood of a DNA match given that the defendant is guilty. And in the denominator, we have the probability of seeing the evidence if he's guilty or not guilty. So the first term is probability of guilt, 0.3 times the likelihood of observing the evidence if he's guilty. That's 100% or 1. And then the prior probability of not guilty times the likelihood of observing the evidence if he's not guilty, which is 10 to the minus 6. And so the posterior, the probability of guilt given the evidence is 0.9999. So very, very likely that the person is guilty. And what this tells us is that the DNA evidence, the data are so precise that it overwhelms any prior opinion that the juror might have. So just to spend one more minute on this example, let's assume that the juror had initially had a prior probability that the defendant is guilty with just 1% probability. So the juror believes that the defendant is not guilty with 99% probability. So if you run through the same calculation, you'll find out that the probability of guilt given evidence, the posterior, is still going to be almost 0.99. It may not go up to 5 decimal points, but it will go to probably 3 decimal points. So it's still 0.999. So the juror has to have a prior that is of the same level of precision that the DNA evidence is, meaning 1 in a million type of precision, which nobody really has. So the DNA evidence is very, very persuasive, and it will automatically lead to a guilty decision in most cases. I'm going to show you a third example, which is now a coin tossing example, where the question is a coin biased, meaning it's not providing even probabilities of heads and tails. So let's start off with what I call an intelligent prior, and I'll tell you why I call it intelligent after a few slides. So on the x-axis at the top, we have the probability of heads ranging from 0 to 1. And on the y-axis, you have the probability or the prior probability in this example. And so what this is showing is that we believe that this coin is indeed biased towards heads, and there is a 60% or greater probability that this coin is biased towards heads. And this is our prior. And then we do a few experiments where we take this coin and toss it a few times. And in the bottom left-hand side, we show a scenario of the posterior distribution. And I'm not going to show you any of the calculations for this, where we have the data of 5 coin tosses, n equal to 5, and 4 of these turn out to be heads. And so what the posterior turns out to be shown here, it shows that the peak is around 0.8, and the distribution is somewhere between 0.6 and 1. And it does not include the 0.5 probability. So we have, with just a few coin tosses, confirmed that this is indeed a biased coin. Most likely, it is going to give you 80% heads. We can do a few more experiments, 8 coin tosses, 7 heads, and now we have an even narrower distribution, again centered around 0.8 probability of heads. Now let's assume the same example, but we start off with not this intelligent prior, but with a uniform prior that is shown at the top of this graph. So we are basically saying that we don't know anything about whether the coin is biased or unbiased, and whether it's biased in one direction or the other. So all probabilities are equally likely. So we essentially are providing no information at all. We have no previous belief about this, and we are relying solely on the experiment. So on the bottom left-hand side, we do an experiment with 4 coin tosses. 3 of them turn out to be heads. And we see that, the resulting posterior has a peak that is around 0.7-ish, but the probability distribution includes the 0.5 value. So we cannot dismiss the likelihood that the coin could be unbiased. We do 5 coin tosses, 4 are heads. And again, there's evidence that this looks like it could be a biased coin, but we cannot dismiss the likelihood that this could be an unbiased coin. So you can see where the trend is going. We need to do a lot more experiments before we can say, okay, it's clearly a biased coin, and statistically, it's unlikely that it's unbiased. And the third scenario, what if our prior is very, very, very precise? So what I'm showing here is what is called an overconfident prior. And just for the sake of visibility, I've made the distribution in the top graph a little bit wider than it really is when I ran the calculations in Excel. So this prior is centered very sharply around 0.5. So our prior is saying it is completely an unbiased coin, and I am virtually certain, 100% confident that this is unbiased. And now let's see our experiments. So we come to the bottom left hand side. We do 5 coin tosses, 4 of them turn out to be heads, but the posterior has not moved at all. We are still left with a distribution that is centered around 0.5, and the results suggest that it's an unbiased coin. We now go to the bottom right-hand side. We have done 30 coin tosses, 29 of them are heads, and yet the posterior is still saying that this is an unbiased coin. And it's being driven by our overconfident prior, meaning that our prior belief is so impervious to all the evidence to the contrary. So we are continuing to maintain that this is unbiased, even though all the experiments are suggesting that it is clearly a biased coin. A couple of things I want to say in all of these examples. So there is a phenomenon called shrinkage in Bayesian statistics. So the data moves or shrinks towards the prior, and the prior moves towards the data. And so the posterior is typically some mixture of this and somewhere in the middle. If the prior is very strong, meaning the prior is very precise, then the posterior will be driven by it. So it shrinks towards the prior. If the data are precise, the prior is weak, then the estimate moves towards the data. And so we saw in the case of the DNA example that the data are precise, and so the estimate is driven by the data. And in the case of the overconfident prior, we saw that the final decision is driven by the prior and not by the data. So what does it mean for us? An intelligent prior combined with few data points, just a few coin tosses, converges quickly to the solution. And we decide, okay, it's a biased coin. If you have a uniform prior, then only the data are guiding the posterior. The prior is providing no guidance. And so we'll reach the answer, but after a lot of experiments. And if you have an overconfident prior, that is not sensitive to new information, then we are essentially going to end up with a wrong answer, most likely. So, implications for exposure assessment, we really need to be like the intelligent prior example, meaning we don't need to have a very, very precise prior, a very narrow distribution. We can be in the direction of where we want to be. So, if you remember, we said, okay, 60% or greater probability that this is going to give you a heads, but we don't have to be really narrow in our probability distribution. And that will give us the right answer, even with just a few data points. The overconfident prior is where we don't want to be, where we come up with a wrong prior that is also overconfident and it's driving the final answer.